Okay, so we're back, and this is the example that we had from last time, where f of x was equal to 3x plus 5 over x squared minus 4. The denominator told us that we had two restricted values, x equals negative 2 and x equals positive 2, and hence this is where the vertical asymptotes come. By looking at the limit as x goes to infinity, we saw that the denominator is stronger, and through by dividing out the limit as x goes to negative infinity and positive infinity, then we're equal to 0, which led to a horizontal asymptote of y equals 0. But there are lots of other limits that we could talk about. And one that's really important is limits at asymptotes. And we're going to do this by reading graphically. We could construct a table of values as we did with our basic rational function. What we were doing in our basic rational function, we were really looking at what is happening as x goes to 0, because that's where our asymptote was from the right-hand side. And from the right-hand side, we saw that as x was getting closer to 0, the function itself was taking off to positive infinity. Versus if we looked at what happened as x was going to 0 from the left-hand side, so here's the left, and I'm approaching from the left, the function was diving to negative infinity. And this isn't a key behavior about graphs around asymptotes. They will act erratically. So let's try and determine the limits of our asymptotes. Okay? So the limit, let's examine what happens as x goes to negative 2, and let's go from the left-hand side. Okay, so from the left-hand side, I'll just put the negative sign there. And I'm just going to write f of x, knowing that we mean this function. Okay. So here's the line, x equals negative 2. It's our asymptote, and I want to see what happens as I start from the left and I approach. Okay. So I'm starting from the left, and as I approach from the left, the function is diving to negative infinity. Alternatively, so it is diving. We could look at the limit as x approaches negative 2 from the right-hand side of our function. So here's negative 2. I want to come from the right of it, okay? Not all the way over here. Don't go past this end. So start somewhere from the right. And as I'm approaching negative 2 from the right-hand side, the function is taking off to positive infinity. So we can write it like so. Let's practice another. Okay? We could ask ourselves about the limit as x approaches now positive 2 from the right of our function. And we'll put an equal sign so we can say what we're talking about. Okay. Now, here's the line x equals 2. I want to approach it from the right. So I need to move to the right of 2 and see what happens to the x values. Okay, I'm moving towards 2 from the right-hand side. But as I'm doing that, the function is taking off to positive infinity. We could also ask about what's happening as x approaches 2 from the left. putting that little minus sign there to denote that, of our function, and that is equal to, okay, so here's the line x equals 2. I want to be to the left of it. Okay, so I start in here, don't cross the other asymptote, and as I'm approaching, the function is diving to negative infinity. So I hope this example gives you some clarity on how to read limits around asymptotes given a graph. Okay. But other things, of course, can happen in rational functions. And one of them is called another quality is called a removable discontinuity. I suppose I should talk about continuity for a second, just to give you a brief idea. In this corner, if I just look for values greater than 2, the function stays smooth. And another word for that is continuous. They're closely related. Also, in between -2 and 2, there's not a problem. I can trace the entire function. However, if I wanted to look on the domain from 0 to infinity, I could start here, but I would have to break the graph and pick up again after 2. On that domain from 0 to infinity, this graph is not continuous because I could not just smooth right over the graph. There's a more technical definition, which we can look at later. So, when it's not continuous, that's also called discontinuous. Okay. And it turns out that discontinuity is not removable. Okay. Let me show you an example of one that is, and I hope that will give you a stronger understanding. So for example, let's try and deal with the function, the rational function, x minus 3 over x squared minus x minus 6. Now first of all, we want to find the domain. Okay. So with that, we're going to take the denominator, x squared minus x minus 6, and find out when that equals 0. Okay. Because when it equals 0, those are values of the domain that we need to exclude. So this is a simple factoring exercise. So this is x minus 3x plus 2. Then using the zero product property, when two things are multiplied together, either the first equals 0 or the second equals 0. So x is equal to 3, or x is equal to -2. And these will be our vertical asymptotes. Well, these will be, let me take that back. These will be our restricted values. So our domain is the set of all x, such that x cannot equal 3 and cannot equal -2. This is the domain. I say these now are restricted values as opposed to horizontal or vertical asymptotes because of this. Let me write f of x in its factored form. So f of x is equal to x minus 3 over x minus 3 times x plus 2. Okay. Once I write it this way, I hope it's clear that f, our function, is not written in lowest terms. That is, there's some canceling that can occur, and I could rewrite this as, remembering there's a 1 up top, f of x is equal to x plus 2. We just have to add this caveat, this distinction, that we have to remember that x cannot equal 3. And this is really helpful for us, because this resulting function, I call it a simplified function. This is our simplified function. That's a terminology I use. Okay. So our larger function is actually going to act just like this function, except at this value. And why is that helpful? Well, this is just a translation of a parent function. In this case, what this is that I'm affecting the x value by adding 2. So remembering our acronym of LARS, if I'm adding, then I must be moving left. So our basic parent function, 1 over x, looks like so. So our translated function has to also move everything to the right. I'm sorry, to the left. We are adding, so we're moving to the left. So this asymptote is no longer at x equals 0. I can simply translate it over now to x equals negative 2. The horizontal asymptote will remain, but since it's a horizontal, just moving things over 2 units won't affect anything. So the horizontal asymptote stays the same at y is equals 0. And then every point over here also shifts over 2 units. So we can just sketch the graph in like so. Now it's bounded by this asymptote, negative 2, instead of by x equals 0. And every point over here will also move over 2. Except we'll have this problem when x equals 3. So every point will shift over until we get to x equals 3. And that value does not exist on the graph. And this is the graph of our original function, this is the simplified function, which is just a translation of our y equals 1 over x, our parent function. There are no x-intercepts. There is a y-intercept. We could label that. To do that, we let x equal 0, and we get 1 over 0 plus 2, which is 0, 1/2. We we can also find out what happens where, if this coordinate did exist, where would that hole be? If we try and put 3 into the original function, we will get f of 3. 3 minus 3 is 0. That's fine. But clearly from here, if we let x equal 3, this goes to 0. And we get 0 over 0. So the original function is not helpful. This is again where the simplified function comes in. So if x were to equal 3, I would get 1 over 3 plus 2, which is 1/5. So even though this circle, this point, does not exist on our graph, we can determine the exact coordinates of what this would be. Again, we could ask about limits. The limit as x approaches -2 from the right. Actually, let's go from the left of our function. As I'm coming at it from the left, the function is diving to -infinity. We can also, this is helpful for us in this case, we don't have to just ask about behavior of limits at positive or negative infinity or around x values of asymptotes. We could ask about limits, say, now in this case, what's the limit as x goes to 0 of our function? Now notice I'm asking about a two-sided limit here. So let's just look at the one-sided. As x goes to 0 from the left, the function approaches a value of 1/2. Hence we have the point 0, 1/2. And the same thing, if we look in between this hole, as x goes to 0, from the right-hand side, the function is also approaching this value of 1/2. Let's try again. Let's look at the limit as x goes to 3 of our function. Okay. So now, I'm not worried what's happening at 3 precisely because I know the graph does not have a value there. Okay? If it did exist, it would be 1/5. So as we go at 3, starting on the left and coming in, the function is also approaching the value, and the value that the function approaches is that point 1/5. Okay? The same if you tried to approach 3 from the right-hand side. So as I'm going to 3 from the right-hand side, the function is increasing, increasing, increasing until we would, if that graph existed, and at that point, the function would have a value of 1/5. And this is why this graph is said to have a removable discontinuity. Because yes, if I was to trace it, I would have to stop and pick back up, but it would be in a smooth line. Versus, like say here, we have a discontinuity at 2, but I would have to jump up and be at completely opposite ends before we move on. So the left and right hand limits do not agree here. Versus, in a removable discontinuity, the left and right hand limits we're approaching the same value. Okay, let's try another one. So, for example, we have f of x is equal to x squared minus 1 over x squared minus 2x minus 3. We're going to try and graph this whole thing. Okay. So there's a lot of processes to go through. Let's find intercepts. So let's find the y-intercept. So our y-intercept is going to be negative 1 over negative 3. This is f of 0. So our y-intercept is 0, comma 1/3. Okay? I just let x equal 0. Now, for an x-intercept, we have to let the function equal 0. And anytime we have a rational function, we need to get the x's out of the denominator. So I will multiply through by the denominator to clear that on both sides. Think about that as over 1. And now these will cancel, which leaves us with x squared minus 1. And 0 times anything is just 0. And so x squared equals 1. So x is equal to plus or minus the square root of 1, which is just plus or minus 1. Okay. So from there, we will get x-intercepts at 1, 0 and negative 1, 0. So we know we have these points on the graph. Let's find the vertical asymptotes. Okay. The vertical asymptotes come when the denominator equals 0. So let's set this equal to 0 and find out when that happens. This will factor to minus 3 plus 1. So we'll have a vertical asymptote when x equals 3 or when x equals negative 1. These are our vertical asymptotes. Now we need to find the horizontal asymptotes, or the end behavior. So we're asking about what's the limit as x goes to infinity of x squared minus 1 over x squared minus 2x minus 3. So if we try and do a direct substitution, we'll get infinity squared over an infinity squared, and there'll be different types of infinity. So let's try and look at the limit as x goes to infinity, but now let's reduce everything by the highest power of x in the denominator. Okay. And the highest power of x in the denominator is x squared. Now the limit as x goes to infinity, now let's reduce these. This becomes 1 minus 1 over x squared over, again this becomes 1 minus, now 2 over x, okay, there's a single x there, that leaves an x, minus 3 over x squared. Now let's see if a direct substitution of reasoning will help us. As x goes to infinity, 1 does not have any x's. It is constant, and so it will stay 1. On the other hand, here, if we have 1 divided by an extremely large number, that goes to 0. And we can use that reasoning here as well, and here as well. So now that we've taken the limit, it looks like 1 minus 0 over 1 minus 0 minus 0, which is 1 over 1, which equals 1. And this is our end behavior. And therefore we can say we have a horizontal asymptote when y equals 1. But let's be careful here. Okay? Do I know that these are horizontal, or that these are vertical asymptotes? I don't know. Okay? We could be in that case where we have a removable discontinuity, and these are simply restricted values. So to double check if I have a removable discontinuity, I will need to write f in its factored form. So f is equal to x squared minus 1 factors into x plus 1, x minus 1, and the denominator here factored into x minus 3, x plus 1. So now we can see that f is not written in its lowest terms. We could cancel these. And that will mean this is not a vertical asymptote, but this value will give us a removable discontinuity. And our simplified function is x minus 1 over x minus 3. We just have to have the caveat that x cannot equal negative 1, because that's where our removable discontinuity is. And this, then, is our vertical asymptote. Okay, now let's try and put it all together. All right. So, what do we have? We have that we have, what do we have? So our vertical asymptote is at x equals 3. Okay, so let's put that in. Labeling the equation at x equals 3. We also have from here, our end behavior is that the limit as x goes to infinity is 1, and that gives us a horizontal asymptote. Its equation is y equals 1. We also have a y-intercept at 0, 1/3. So that is below this line, 0, 1/3. And remembering from here, we have a removable discontinuity when x equals negative 1. So at this point, we're going to have some type of problem. We're also going to have x-intercepts from here at 1, 0 and at negative 1, 0. Okay, so I'm just thinking here for a moment. Perhaps we should put this in Desmos so we can all look together and see what's happening here. The clearer view. Okay, so we want to graph this function. So the numerator is x squared minus 1. Okay, so that's just our basic parent function translated down 1. But now we need to divide that by x squared minus 2x minus 3. And close that. Okay. Okay. Now, what I'm looking at, and perhaps you saw me zooming in, is I'm looking at what happens at x equals negative 1. Okay. So clearly we can see on this graph, let me try and put a point down, negative 1, comma 1. Or negative 1, comma 0.5, sorry. And when I do that, we clearly see that that graph is on there. So one thing that we did is when we found here our x-intercepts, notice we had not determined what our restricted values were, nor if this was in lowest terms. And it turns out this minus 1, this is part of the restricted values. Okay. So in fact, it's giving us a false negative, but there's a restricted value there. Okay. Because it's a removable discontinuity. So perhaps to see this, let's look at our basic function, our simplified function, f of x is equal to x minus 1 over x minus 3. Then in this case, f of negative 1 exists we get negative 2 over negative 4, which is a positive 1/2. So in this case, we get negative 1 comma 1/2. But this needs to be an open circle. And then finally, we just have to figure out if the graph lives up here or down there. So we need to pick a value on the other side of x equals 3 to evaluate and find out. Say 5. I don't care. Then 5 minus 1 is 4. 4 divided by 2 is 2. So we get the point 5 comma 2. And so our graph would look like that. All right. This will take some practice. We have one last example. This is the oblique asymptote. Okay. What are known as oblique? Okay, so for example, f of x is equal to 2x squared minus 5x plus 4 over x minus 1. This will not factor. Certainly not factor into x minus 1. Okay, so we can concur. So there will be no canceling, and our vertical asymptote happens when x equals 1. We could try and ask about horizontal asymptotes, and again we'd be looking at the limit as x goes to infinity of 2x squared minus 5x plus 4 over x minus 1. Again, if we do some type of direct reasoning here, we have this is some type of infinity divided by another type of infinity. So let's do the same trick that we've been doing, and we'll divide through by the highest power of the denominator. Okay. So in this case, we'll be dividing the highest power is x in the denominator. And if we simplify that, we get the limit as x goes to infinity, now of 2x on top minus 5 plus 4 over x over, this becomes 1 minus 1 over x. And now in this case, let's do the substitution. 4 over x will certainly go to 0. 1 over x goes to 0. 5 will stay. 1 will stay. But the problem becomes here. If we let x go to infinity, we're still talking about some type of infinity over 1, which we don't know. And in this case, we will end up with an oblique asymptote. Sometimes it's also called a slant asymptote. Okay. And some of you may remember how we find these from college algebra, we're going to have to do the long division. Okay, so x minus 1 goes into 2x squared minus 5x plus 4. To do the long division, we ask how many times does x go into 2x squared. Doing the reduction, that's 2x times. So 2x. Then we have to take that, our 2x, and multiply it by everything out here, which is equal to 2x squared minus 2x. This is what gets written down here. Then following long division, I'll need to subtract, which means I have to change the signs. Then 2x squared minus 2x squared goes to 0. Negative 5x plus 2x is negative 3x's, and we can bring down the 4. Then we can start the process again. How many times does x go into negative 3x? That reduces to negative 3. So we write that as subtract 3 up top. Then we have to take negative 3 times x minus 1. That's equal to negative 3x plus 3. That's what we write here. But remember, we have to subtract. So when I'm subtracting, I need to change the signs. Then negative 3x plus 3x goes to 0, and 4 minus 3 is 1. This is our remainder. But what this tells us then is that our quotient is our asymptote. Y is equal to 2x minus 3. Okay, so let's put this all together. Let's try and graph it. We have a vertical asymptote at x equals 1. We also have an oblique asymptote when y is equal to 2x minus 3. So 2x minus 3 has a y-intercept of minus 3. Let's put in y equals mx plus b and a slope of 2. Given our original function, what was it? Our original function was f of x is equal to 2x squared minus 5x plus 4 over x minus 1. And let's try and find a y-intercept to give us 1 point to deal with. So if we let x equal 0, this will go to 0, this will go to 0, so we're left with f of 0 is 4, this goes to 0 over negative 1, which is negative 4. So our y-intercept is 0, negative 4. And that puts it down in here. And now here is where we're just sketching. Okay. So that bounds this graph in between here. And once it's bounded in between here, look at the reflected angle in the graph as a good sketch will also be bounded in there. We could look for x-intercepts. That is, we would have to solve 2x squared minus 5x plus 4 equals 0. And what we'll find out is that this has no real solution. And that is why there is no x-intercepts. Alright, so there's a lot to rational functions. I'm sure you have questions, so please send me an email and give it a shot.